Good, yeah. So we're going to touch a little bit on waves and sound this afternoon, right? And before we can get to the subject of sound, um, we want to talk a little bit about waves first, because sound is a kind of wave, right? And then in your, your workplace, your everyday life, at home and so, you encounter waves all over, all over, right? Um, there are all kinds of waves that you see all over in nature. There are waves all around you that you don't realize, and so, right? Um, just what is a wave? What's a wave? And a very, what would I say? So layman's definition, right, is like as the notes brings out there, it's a traveling disturbance, right? It's a traveling disturbance, disturbance, right? And you see examples of that all over. Water waves, right? It's a disturbance in the water. You throw in maybe a pebble in a pool of water or a container of water, and you see waves being formed. The reason why that happens is because you disturb the nature of the water, the surface of the water, and you create waves, right? And um, of course, if you're near a river, if you look out at sea, you see all these what we call water waves, right? And water waves basically is a disturbance of the water because of wind and water current. And so all of that cause that disturbance, right? The whole weather cycle, right? That creates these disturbances in the atmosphere and with the wind, and so creates water waves and all of that, right? And coming to that, a second point is made here about waves is that they carry energy. Waves carry energy, and this is so important, um, right? From one place to another, and this is attracting a lot of attention in some circles now, where they're thinking of harnessing the power of waves, right? As a matter of fact, sometimes we use the word so strictly. You think that when you hear wave, you only think of water waves, right? You think of water waves, but there are so many different types of waves around us, right? And you're going to hear of, we're going to come to sound, sound waves. You're going to hear of radio waves, right? Radio waves. Um, as a matter of fact, radio waves and microwaves and all that is a broad category. Something called electromagnetic waves, right? There's a broad category of waves that include radio waves, include microwaves, include um, the wave. Well, light is an electromagnetic wave, right? There are two schools of thought when it comes to light, right? There are those who thinks that light it behaves more like a particle, but we're not going to consider that at all. Um, but then in the school of there's another school of thought that says that um, light behaves like a wave, right? It has certain characteristics of waves, right? And later on, and so if you study waves, um, you will learn of reflection of waves and refraction of waves, and there's something called diffraction of waves, right? And some of those terms we're going to hear them a little more in connection with light waves when we do mirrors, and lens, maybe possibly Friday coming, we'll make a start with that. We'll consider light waves in detail, right? So yes, there are all kinds of waves. So don't think when you think of waves, only think of water waves, right? Don't think of just water waves. They have different types of waves. As a matter of fact, um, they're two. They don't categorize, or I should say, they categorize waves in terms of how the wave travel, right? And there are two categories really. One, they call it transverse waves, and two, you have what you call longitudinal waves, right? So these are two broad categories of waves, right? And just a little definition, right? Let's see if I can move this a little. Transverse waves. Remember we said that a wave basically is a disturbance and it carries energy from one place to another, right? And a transverse wave really is one in which the disturbance occurs perpendicular to the direction of travel. So the disturbance is perpendicular. For disturbance is perpendicular to direction of travel, right? And you see this a lot. If you were ever to see, okay, an electromagnetic wave being graphed, right? What you would see is that the wave is going to be, it's traveling this way, but the wave is moving up and down, right? While it's traveling that way. So in a transverse wave, what's happening is that the wave is moving, whether it involves a certain medium, right? Or whether it involves an interplay of an electric and a magnetic field. And that's kind of heavy, right? I'm not going to get into that really, right? Whether it involves that or whether it involves a physical medium. Y'all ever see when you were kids, maybe you buy, these slinky springs? Your parents ever bought that for you, or you ever bought that for your children? Slinky springs? Y'all ever see something like that? It's a kind of it's a springy plastic what would I say?
I know what the spring is. Sorry, it was just never bought for me.
Okay. But you can create a wave with even, let me go with even a rope, you take the rope and you give it a disturbance, let it go like this. Have you ever taken a ribbon? You can take a ribbon, right? And you create a pattern like this. Those girls that do little twirling and so with ribbons, right? What's happening is that the medium, which is the ribbon itself, is moving up and down, right? But the wave is traveling that way. So while the ribbon is moving that way and the ribbon is moving this way, and it's going back that way, it's going back this way, and then it kind of dies off towards the end. But the energy that you give the ribbon here travels in a to and fro motion, right? Up and down, perpendicular, right? But what happens to the energy? The energy travels from here and goes here and goes here, and it kind of dies off at the end there, right? So the energy travels this way, right? But the ribbon goes up and down, right? That's a very, very simple example of a transverse wave, right? That's a very, very simple example of a transverse wave. Now, what about a longitudinal wave? A longitudinal wave. Oh, and by the way, when it comes to transverse wave, there are more transverse waves than any other than the other type, the longitudinal type, right? Because, as I said, light. Oh God, I spelled the word L-I. Is it H, right? Light is a transverse wave. All the waves you know about, the waves that take our the microwaves that you use to cook food, microwave, right? All the electromagnetic waves, that you use for radio transmission, right? They're called radio waves, right? Microwave, radio waves, all the light is an electromagnetic wave as well. All of them are electromagnetic waves, and they are all transverse waves. Transverse waves, right? And they are all produced by an interplay of magnetic and electric fields, right? Fields. So yeah, they're all created by an interplay of magnetic and electric field, right? So we can't. I mean, this is just a course. You're just being made aware of certain things, right? We're not getting into the depth of it, but just know that most waves that you know, right? Um, the water wave that you see on the in the river, it's a transverse wave, right? Light waves are electromagnetic waves, which are transverse waves, right? Microwaves, not just the wave that the microwave in your house, right? The microwave oven or what you call it at home. No, microwaves are used in all kinds of things, right? That's how I think I think they transmit certain signals and so with, right? Microwaves. No, don't think it's just the one. It all has to do with something we can talk about later on, the frequency and the wavelength and so, right? Radio waves and so all of them are really electromagnetic waves, and all electromagnetic waves are transverse waves, right? Now, what about longitudinal waves? Longitudinal waves. These are rarer, right? These are rarer. And in a longitudinal wave, what happens? The disturbance is parallel to, this is an error, parallel to the travel, or direction of travel, right? The direction of travel of the wave, right? So the disturbance is in the same direction as the travel. And a good one, that's what I was talking about, that's slinky, right? That's slinky. Let me see if I can, wait. I'm gonna try to see if I can cut the one that they have. Let me take a picture of this one. Copy it there. Let me see what here. Okay, good. Look here. So if you take the slinky spring, right? You take the slinky spring and you were to give it, you notice here, in part A, you give it you kind of give it some energy, right? And it creates a compression. And then that compression travels along. Look in B, the compression ends up here, right? and then the compression ends up to the end, and then sometimes if somebody else is this end, the compression turns back now and heads back to your hand, right? And that's how I remember when we were kids and we were doing waves in school. We all brought these slinky springs in school, right? They're made of plastic. And then we'd play and we'd make the transverse wave, we'd make the longitudinal wave, right? So in this case, you give it a compression and that compression travels. Of course, you give it some energy, right? And that energy, that little shock that you give it, right? Creates a compression here. And because the spring is such that it can't keep the energy to itself at one place, right? So what it does, it kind of sends the energy down and it creates a compression a little further down, right? And then it travels sometimes to the end here. And then if somebody is here, the compression returns to you back, right? And some we would play, you and your friend would play and let the compression go back and forth. That's an example of a longitudinal wave. The reason why is that the compression is um, actually traveling in this direction. And the wave also is traveling in that direction. The wave also is traveling in that direction, right? So, and even when the compression is coming back in this way, right? It's still parallel to, the direction of the wave, right? So sometimes the wave comes back this way as well. Compression comes back to you, the wave travels back to you, right? So this is a good example of a longitudinal wave. And the most famous example, the most famous example of a longitudinal wave is what you think? Anybody can guess? I know you get some people in this class who know a little bit of physics. What's the most famous longitudinal wave? Nobody can say? The most famous longitudinal wave is song. It's song, right? Because that is what happens when you speak, right? When you speak, and we can come to a little bit more on song in just a moment, right? Um, when you speak, what happens is that remember your vocal cords in your throat, that vibrates. And how it vibrates? It vibrates um, as air comes out of your lungs and it causes that vocal cord to vibrate. Um, just like, well, kite season, we just had kite season, right? And you all know the kite just get a thing, we call it booming. uh, Anybody know what I'm talking about? There's a thing that make the kite sing.
The bull soar.
Huh? What you call it?
The bull.
The bull? Okay, we just call it booming. I guess from the song we were little, we don't know what really to name the thing, right? But because it used to go a kind of woo, song, we just call it a booming. Right? Yes. Yeah. So just to give you an idea um of how song waves really operate, let me again let me cut a little picture for you. Let me cut a little picture again for you. All right, and they compare it to that slinky spring again, right? No, 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 not that one. Yeah. All right, look here. So this is what a sound wave, what it's doing to the ear, right? So here it's like a little speaker, right? And you can imagine this to be your vocal cord, right? In your throat that actually creates sound as you speak, right? And what happens really is that as well, let's use a speaker, right? When the speaker is given some kind of, electrical disturbance, right? And it causes the diaphragm on the speaker to, and if you watch, I don't know if y'all ever you ever see a speaker without that mesh in front. You see that paper cone, right? Most of them are made of some kind of paper, right? You see the cone moving in and out. Anybody ever got the opportunity to look at that and see? Anybody ever saw a speaker without that protection in front? Have
Yes,
you ever
sir.
seen the diaphragm? The diaphragm actually moves in and out, right? And that creates compression, right? And they use two words, compression. Let me write the words out here. Compression, that's what you're seeing here, here, and here. It creates compression, right? And then when it's compressed, it creates a kind of, a pulling apart of air here too, in these areas here. And they call that rarefaction, rarefaction, not fraction, rarefaction, right? This should have been a little closer. Yeah. So you have alternating compression and rarefaction. And that is what causes the air to move in a certain way. And then when it goes to your ear now, right, from the speaker to your ear, it creates that same movement that the diaphragm was making in your inner ear, right? Your what we call the eardrum, right? And your eardrum would vibrate the same way that diaphragm on the speaker is vibrating, right? And then that would transmit in your inner ear. And so we're not going to get in too much into that. Our course doesn't allow, so much of detail, right? It's interesting if we had gone into the design of the human ear and how amazing it is. Anyway, that also when your eardrum vibrates as well, right? It sends certain signals straight to your brain, and your brain interprets the sound, right? So I brought this up because sound waves are a very good example of what we call longitudinal wave, right? Longitudinal wave. Keep that in mind. Um, I want to go back because your course outline talked about certain features of a wave, and I just want to mention those, right? I just want to mention those. So we talked about examples of transverse waves. We talked about examples of a longitudinal wave, right? So we're going to get into a little bit of what we say. We want you get familiar with certain terms that we use when it comes to study of waves, right? So let me highlight these here. On the diagram. Good. It's not pasting. Nope. Aha. Good. Good. It's too large now. Good. So there are some terms you're seeing here. There are some terms you're seeing here that you want to get familiar with, right? So here, here, you're seeing a wave described, right? It's being described in terms of, well, where it is at a particular time, right? At a particular time. And you're seeing something that, okay, the distance from here to here, right? So this will give you distance. This what do you call it? The horizontal axis is really telling you the distance that the wave is traveling over a certain, we're just taking a snapshot at a particular time. So don't mistake the horizontal axis as the time axis, right? And in this case, you're seeing that that distance for the wave to make a complete oscillation is called a wavelength. It's called the wavelength of the wave, right? It's called the wavelength of the wave. And the symbol there is a symbol called lambda. Lambda is a Greek, is a Greek letter, right? So when a wave is described in this way or graphed, let me use the word rather than say described. If it's graphed this way, where the horizontal axis shows the distance, please note all of this, right? When the distance is here, right? And here, this is what we call the displacement. Down here is the displacement of the wave from the rest position here, right? So what you're going to call the distance between successive points that are at the same level. You say that, well, okay, sorry, this is a complete oscillation. The distance for one complete oscillation is called the wavelength of the wave, right? You see a little a here? This distance here, the displacement from the rest position to the lowest or to the highest, is called the amplitude of the wave. Right? Good. Now, what about if you were to describe the wave now, and we take it at a particular location, and we plot the time on the horizontal axis, and the displacement of the wave from the rest position. Right down here is the displacement again. Right? But notice we are using the horizontal axis as the time axis. You get another bit of information, right? And the time that it takes to make one complete oscillation. It goes up, comes back to the rest position, goes in the opposite direction, comes back to the rest position that it started at, right? This is a complete oscillation. That time is called a period, right? And again, this will show the displacement from the rest position here to here is the amplitude. No change there, right? There is a related quantity called the frequency of a wave, right? And the related f, which is the frequency, to the period, right? What really is the frequency? The period is the time for one complete oscillation. The frequency, on the other hand, is how many oscillations you will get in 1 second, right? And it's measured in hertz, Hz, right? It's spelled Hertz, right? And the symbol is Hz, right? I think there's a scientist by the name of, his last name was Hertz, right? So they, as a tribute to the work that he did with sound waves, they said, man, let's call or give the unit of frequency. Let's call it after him, his name, right? Hertz. So these are some terms you will hear, right? When you talk about sound waves in particular, right? Oh, by the way, all waves, you will have wavelengths, and the wave will have an amplitude, it will have a certain period, it will have a certain frequency, all waves, right? But we can concern ourselves a little more with sound waves, right? Um, but before we go away, maybe I can pull an example. Let me pull an example from the notes, just for you to get an idea of the wavelength of radio waves, right? Just 1 second. There's a little example in the notes. Give me 1 second. I want to put on my lights as well. Place is getting dark. 1 second. I'm sorry about that. I went over and I clicked the wrong switch, and I cut off my the power to my computer. Just give me a second. Let me get my whiteboard up again. Is my recording on still? Yes, I think it's still on. Yeah. Sorry about that.
Sir, are you okay?
Yes, I actually took off my power to the entire computer system without thinking what I'm doing. You're right to ask me that. I went over and to put on the light, and instead of putting on the light, I took off the switch. All right. Here, these things happen, you know. You get old, all kinds of things happen to you. Good, yeah. So I don't know if you're familiar long ago when they used to transmit radio waves using what we call AM, right? And the AM means amplitude modulation, right? Because what it actually would do they would actually take the song and let it ride on the amplitude of the other wave, right? That they will use to transmit the radio waves with, right? Now they don't use amplitude modulation. They use what we call frequency modulation, right? And they're giving you an example here of the difference in terms of what do you call it? The wavelength. They want to show you the wavelength, right? So they give you an example, right? So they have AM and FM radio waves. They're both transverse waves, right? One of them is traveling at a speed of, both of them are traveling at a speed of 3 times 10 to the 8 meter per second, right? And one station is broadcasting AM radio wave, and the frequency is 1230 times 10 to the third power hertz, right? And the FM frequency is 91.9 times 10 to the 6th hertz. Notice this is a much higher frequency, right? They want you to find the distance between adjacent crests in each wave. And there's a relationship between the wavelength, the velocity of the wave, as well as the frequency of the wave. And here they put it in all they put in all the information inside of the formula. And you see that the AM signal has a wavelength of 244 meters, while the FM wavelength, notice how small it is, right? Right? Notice how much smaller it is, right? And nowadays, they don't use AM, right? They don't use AM signals anymore. They use FM, right? They use FM signal. And perhaps for your own edification, you can research why one is used over the other. What's the advantage? I mean, both would have their advantages, right? Both would have their advantages and disadvantages. And you can probably research why that is so. But here's a good relationship to know, right? Lambda is equals to V over F. And we also covered another one just now where there was which one? F equal 1 over T. And of course, if you rearrange this, you'll see that T is equals to 1 over F, right? So these are useful relationships that you can use to do calculations involving waves, not just sound waves, any type of waves, right? Any type of waves. So we want to switch over now to talk in particular about sound waves, right? And because that's what we're concerned with more. At least we'll talk about light waves and so a little later when we do mirrors and lenses and so, right? So let's talk about sound waves a little. Sound waves, right? And sound waves, they have different frequencies of sound waves that we can hear, right? They say that the human what do you call it? The human ear, right, can detect a certain range, right? A certain range of sound from a certain frequency to a certain frequency. And well, they say that, well, okay, your ear can detect from 20 hertz to 20,000 or 20 kilohertz, right? Not everybody. That is not really so for everyone. Most of us may not be able to detect that, nor this, right? We're somewhere in the middle, right? They're somewhere in the middle. The lower, the lower, the lower frequencies, what you call infrasonic waves, right? Infrasonic waves. And certain animals would communicate using those frequencies, right? And I think the notes refer to the rhinoceros, that they would usually use these very, very low frequencies. So you wouldn't hear them. It might just be a low vibration that they're emitting, right? Whether from their nostrils or where, right? And it will actually travel, and well, other rhinoceros, because their ears can detect it, well, they'll know, right? Y'all ever see how, okay, I've seen a video one time. It was one of these nature shows, right? Where all of you know that when alligators, right? Y'all hear how alligators communicate, and they make a certain song, not so?
Yes, sir.
They make a certain song. However, in this nature show, they were showing you how the alligator would also vibrate its body, right? It'll vibrate its body at a very low frequency too, right? It hardly makes a sound. But guess what? Another alligator, right? In another, some distance away, a mate, right? A mate. That song you hear when alligator go coo, 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 that song actually is more for like mothers and children, right? But this vibration I'm talking about, the documentary pointed out that it's how they attract mates, how they let a, a mate know where they are, and whether they're coming or whether they should come and meet them, or I don't know what they're talking to one another, but they use those infrasonic waves, right? Those infrasonic vibrations, like, right? So those songs, we can't hear it, but it's happening, right? It's happening, right? Yeah, and then there's what we call on the higher end. These are what we call ultra sonic waves, right? Um,
Yes.
yes. So I think I'm using a wrong word. I shouldn't say waves here. We're talking about waves in general. It's frequency, frequency. I need to correct myself. Frequency, right? Yes. And these here, for those, I think some people in the class, they're into the medicine and so, right? Um, and they use that to be able to detect what's happening in the human uterus and so, right? And they'll know, they'll be able to, the computer is going to be able to interpret the bouncing off of those frequencies on tissues that are inside there, and would actually create an image, right? That the doctor would see and tell you, oh no, the baby, yes, the baby moving, the baby is there, right? And you can even know whether it's a male or a female and so inside there, right? So yeah, they have their uses, right? In nature, you see a lot of infrasonic frequencies, right, between animals communicating with one another. I think um, bats use also ultrasonic waves for locating their prey, and how to fly about in the night, even in the dark, right? Call it sonar, right? As a matter of fact, one time I had a bat problem upstairs in my house. The guys did a bad job in my roof, and bats were in there, and I took an ultrasonic frequency from that is recorded on YouTube, and I played it, and the bats got very confused and started crashing into the wall and all things. Yeah, One time I even had, I'll tell you this, you laugh. I had a problem where a rat went into my car engine, and I used an ultrasonic recording on YouTube, and I played it. And guess what? The rat couldn't bear it. The rat ran out of the car. Yes. Yeah. So yeah. So some of these animals, they're sensitive to these ultrasonic frequencies, right? Some of them, some animals use it to their advantage. Others are affected by it negatively, right? Yeah. Um, good. So what else we want to talk about with song? Song. Let me just give you a little picture again of how the sound wave can be graphed and so. All right, just 1 second. No. Mm-mm. Good. Yes. Look here. So again, if you have like a speaker here, and there's there's air particles in a tube, right? So what will happen um, when, as the music is being played or the song is being delivered by the speaker, right? The diaphragm moves. What will happen? You will have a series of what we call rarefaction, and well, they use the word condensation. Um, I don't know why this author used that word. I don't want to confuse this word, right? Use the word compression, right? Use the word compression. So you have a series of rarefaction and compression happening in the air, and that's how the sound is being produced. And here it is on a graph, right? Here it is on a graph. They're showing you how air pressure is varying, right? How air pressure is varying, and it's because of the movement of air particles, right? And and how air pressure would increase and decrease depending on whether there is compression or rarefaction happening, right? That's what we're seeing there. Um, mm, all right, good. So there's this bit here about the speed of sound, right? And there's no one number. There's no one number that um, that we can say, oh, this is the speed of sound, right? Because remember, sound travels by the particles inside, right, or the vibrations inside of a substance is actually compressing and refracting, right? So depending on the material, sound is going to travel at different speeds, right? Depend on, well, like regular air, and then the temperature of the air too. The temperature of the air matters. Like they say, air at air at, and these are 0 degrees. Sound travels roughly around 330 meter per second, right? At 20 degrees, I'm seeing here on the chart, it's all in the notes, right? 343 meter per second, right? And I guess they're trying to say that, well, because of the higher temperature, the air molecules are, moving a little faster, right? And for that reason, sound would travel a little faster at higher temperatures, you know? Yeah. So they have a whole list there. They have a whole list of speeds for sound in different medium, right? In different medium. The plural is media, right? Yeah. As a matter of fact, I don't know if y'all ever in high school, they tell you that you can actually calculate, you can do a rough calculation of how far a cloud is from where you are. And there's a problem inside of in the notes with that calculation. Let me tell you how it works. So you are here, you're on the ground, you are here, right? And there is a cloud up here. And what happens? You might see lightning, right? Now, if anybody knows what really happens when there's lightning, right? There's the source of the lightning and thunder is the same source, right? So light, when you see the light travels so fast, we can neglect the time that it takes to travel from the cloud to you, right? But y'all notice that thunder actually takes about sometimes a second or more, and you hear it after the lightning. Anybody notice that?
Yes, sir.
You see the lightning, big flash, and then you brace yourself, and then you hear this big rumble, right? Good. So what we're gonna do, we're gonna actually, if we neglect the time that it takes for the lightning, for you to see the lightning, because light travels so fast, no need for us to fight up, right? No need for us to fight up. So forget that, right? We're gonna do a rough calculation. So what you do, if you take a stopwatch, right? Like your cell phone, and as soon as you see the lightning, start the stopwatch. And if you start the stopwatch, let's say, and when you start it, and when you hear the thunder, you stop the stopwatch. And let's say it takes 5 seconds, right? Between the lightning, when you see the lightning and when you hear the thunder, it's 5 seconds. Well, the distance of this cloud from you is 5 times, use 330, no other 331, right? 5 seconds by 330, that's the speed of, we're using the rough speed of sound. I mean, the air might be around 20 degrees, right? Meter per second. Is it 330? I use 330, right? 330. Let's say the place cold. So you end up with 5 by 330 is how much? 5 by 330, right? 650 meters away. Sorry, 1,650 meters. So that little experiment can help you to see how far that cloud is from where you are. You think you follow that little calculation? From the time you see the lightning, start your stopwatch.
Go it over, please.
Yeah. As I said, when the lightning flashes, you see the lightning almost instantly. So neglect the time that the light takes to travel to your eyes, right? Neglect that time because it's just a fraction of a second. Fraction of a second. Probably is a microsecond. And you don't see the light. So forget that. Don't factor that in the calculation. So as soon as you see the light, you start your stopwatch. And when you hear the thunder, you stop your stopwatch. In this example, the stopwatch registered 5 seconds. I'm using a nice number, right? Now, if you want to calculate how far the cloud is from you, all you got to do is calculate 5 seconds by 330 because that's how the speed of sound. It came from the cloud and it reaches you, right? The rate at which it's traveling is 330 meters per second. And when you multiply 5 by 330, you get 1,650 meters. That's how far the cloud is from you. Right? It's a nice experiment when I was a little kid. They teach you in high school, you know.
Sir, are you okay?
Yeah, yeah. I'm waiting on anybody to say anything if they follow it or not. All right, good. So we want to now turn our attention to, and this is very important for us, right? Sound intensity. Sound intensity. They're a very important measure, right? In that it's true that when it comes to sound, let me just mention this, right? The loudness of a song is actually connected to the amplitude of the song, right? And the pitch of a song is connected to the frequency, right? These are two important connections you want to keep in mind, right? The loudness has to do with the amplitude. The pitch has to do with the frequency, right? However, what we're very concerned with is what we refer to as sound intensity. And then what intensity does, right? What intensity does, it actually calculates sound intensity equal the power of the song, right? That means how much energy is transmitted per second over the area that it travels, it covers, right? The intensity is equal to the power over the area, right? And they gave a very nice illustration. Let me cut it again, just to bring it over. No. Yeah, this here. So here, let's say this is a speaker box. And you are very close to it. When you are very close, remember, okay, this is the area that this sound is distributed across, right? It's wider than that, but let's just see, right, for the sake of argument. As you go closer to the speaker box, the area here that you see that is marked 1 is very small, right? And if you place your ear somewhere in this vicinity, all this energy that is coming out from this box is distributed over this small area, and therefore the intensity, right? The intensity is going to be much more than here. Look at this second position here. You're further away. Now this song has to fill a larger area. All that energy is dissipated in a larger area, and therefore the intensity is a little less, right? So right away you should understand, and you see it sometimes. Some of you are at a sporting event, or you go to an occasion, you're right up to the box, right? As you say, you're enjoying the beats. But we're going to learn a little later on that it can have a detrimental effect on our ear and hence our overall health, right? So while yes, this quantity I equal P over A is a useful one, and we don't really use it. We don't use this directly, right? What is used more is what we refer to as decibels. Decibels. Decibel. And decibel, we usually will use this symbol for it, right? It's equal to, we go with 10 log of I over I naught. Now, what's all of this? Right? What's this? Now, when we measure the decibel over a song, we use this formula. We use this formula, right? And it's really 10 times the logarithm. And notice it's the what we call the common logarithm. I mean the base 10 there. I can put 10 here. I don't have to, right? The logarithm of the intensity of the song over, and notice here, I naught is like the reference frequency. The reference frequency that we're using, right? And sometimes I naught, right, is actually they might use what you call ambient air, meaning the air around us. What's the intensity of the sound around us? You know, normal air. So they might use that as the reference. Not always, right? Different ways of measuring sound levels might use different reference intensity, right? Good. So from this formula now, you can actually calculate, right, the intensity of different songs. And I'll give you a few examples here. They have a table. Let me just one song. One second. Nope. Good. Look here. Good. So as I said, we're not going to pay attention to the intensity. We're going to look at the decibel, right? Sorry, when I say intensity, in terms of the how much watts per meter square, we're not going to be concerned with that. We're looking at the intensity level, which measures the decibel of the song, right? And you're seeing some numbers here, right? Like leaves rustling. The decibel level is just about 10, right? That's very gentle on the ear. It's actually pleasurable. Whisper, 20, right? Normal conversation, notice this, right? Two people, they mentioned that they're probably 1 meter apart, right? 65 decibel, two people talking, like me talking to you now, right? Well, depending on how you turn up your volume, eh? Traffic, inside, what is inside car in city traffic? 80. As a matter of fact, I'll tell you this, right? I'll tell you this. Somewhere here, going up, right? You may need ear protection. From 80 going up. So as a matter of fact, I think some jobs, right? Some labor laws. Actually, anybody knows in Guyana what's the amount of decibel that we really should be using? We really should be using an ear protection. Anybody knows? Anybody can Google it and see what's happening. Anybody trying it? Is there a law in Guyana as to or maybe that is in the purview of the labor ministry, right? Any one of you work in an environment where you know the sound level is very high? Let's use that.
I'm not sure, but maybe it's like 80 to 85 decibels or something like that. I don't, not sure.
Yes,
Somebody else can check.
it's somewhere there. I want to know if Guyana, right? I'm concerned about you. I want to know whether Guyana has some kind of bylaw that says that if you work in a noisy environment and the decibel level, right, the intensity level is 80 or 90, you should have the workplace supposed to provide you with some kind of ear protection. That's what I want to
Yes,
know.
sir. Yes, sir. It's stated in the
Yes, sir.
Occupational Safety and Health Act.
It's obligation by the EPA too, sir.
Okay, and what number they say? Do they call a number? They give you a number?
There's not
Well,
a
in the
specified number, sir.
Sir, for the Occupational Safety and Health Act, it's stated mostly ranging from 85 to 89. If the range is over, you double your AirPods or you shut down that area that the machine is working with until you have a balance as well. Because you normally have to check it daily, 3 times a day.
Okay, well, you know more than me, Greg. I never heard of that. Yeah,
Yes, sir.
but
I'm a safety officer, so I know
okay,
that.
yes, yeah. I see people working, young boys working with this, you know, this thing we call angle grinder, cutting steel. And don't talk the how hazardous that thing is, you know. The blade is so thin. I'm coming back to the sound aspect, right? I've I'll tell you this, and after that day, I don't play around that thing. I don't use it. If I hire somebody, they want to use it, that's up to them. There was a boy doing some work on a roof for me. He's making a shed. And this guy decided that he don't want to use the shears too long. So he took this angle grinder and he's cutting this zinc. And you wouldn't believe me. This zinc kind of bind the blade and break it. And this blade fly out and cut this boy. You get a vein that's what's called jugular. They get a vein in your neck, let's call it your jugular. Am I right? Medical people. That blade missed the man jugular by probably a couple mm. And he still cut him and he was bleeding and all of that. And I said, oh my, since then I don't play around it. As a matter of fact, there is a thicker blade that is available. It's a little bigger and it's for the bigger angle grinder that doesn't break that easily. But guess what? Nobody wants to use it because it's more expensive. You have to have a bigger angle grinder. But nobody uses it. They use it small. Imagine I pass the Kanji turn in Borbice here, where they're making this road and they're making these what do you call it? These concrete drains. And the steel they're using in those concrete drains is probably about, I average about 3/4 or 1 inch steel. And guess what they're cutting it with? That same little baby angle grinder. I pass and I see the workers. I say, oh gosh, you know, nobody cares about these people. Nobody cares. That boss man's supposed to get the type of angle grinder that will not, you know, break easily. The blade has to be a thick one or find some other way, right? As a matter of fact, speaking, coming back now to our course, ear protection. And if I ask them about ear protection, they want to know what you're talking about. First of all, they're already deaf. By the way, the loudness of their conversation, right, is telling me they're already deaf, right? And these boys, they work without any ear protection, right? I wish who was the person who said they're a safety officer?
Myself, sir.
Yes. Say back the name. I'm seeing the name a little.
Zima Mohammed.
Shazima. Have you
Yes,
ever tested, like, you know the angle grinder that they use? You know what I'm talking about, the angle grinder?
Yes, I know. Yeah.
Or the electric saw?
Yes,
And
sir.
how many decibels that would produce?
Well, I've never personally myself, I've never tested those small scale of noise, but in loud factory like DDL and Banks DIH, I've conducted testing in those areas.
Okay, it's interesting. You know why I say that? You know this Shazima, they're sending you to these big places, but let me tell you, the common people, the common men who are working construction, if you know what they do to those boys and their ears and so on,
Yeah.
nobody cares about them, right? And there's where I think, and they can't form a union. The man could knock them off as soon as they say, man, boss, I got to get earplugs, or man, buy a couple of these things,
Hmm?
Boss man say, what wrong with you? You want me book my boss on his contract? But look, don't come back next week. Yeah? You asking for too much things. That's the kind of response you might very well be getting, right? So yeah, I mean, if you are personally working in a noisy place, it's good for you to. And there is a little instrument. I actually had one here, but I think I don't know if it's in one of these boxes. I had one of these decibel meters, right? Sound intensity meters, and it would actually. I remember when we would go, we would usually have a lot of these big gatherings where we have what we call assemblies, right, and conventions. And I was with sound at the time, and when we set up our speakers and so on, the place we set it up, we usually go like a certain distance from the boxes where people will be sitting, right? Because when you go close up to the box, you will have a large intensity, right? But you go to, all right, let's say somebody is sitting 3 meters away from the speaker. You probably go 2.5, and you test the intensity level, right? And you ensure that, well, it's in the range. You see, Mark, normal conversation. Maybe it's bordering on 80, and so it shouldn't be more than that, right? It should be a little less than 80. And then you know that, yes, the speaker isn't too loud, right? And then sometimes what we do is we walk around during the program, and we'd even have people's opinion, because the meter can very well give you all kinds of readings. But if people say, man, the sound is too loud, man, it's pounding my ears all day, so you would normally want to adjust the level, right? Yeah. So these levels here are from the 80 inside car and city traffic. As soon as I think it crosses over 80, you have to beware, right? And think about your ears, right? Is it a car without muffler, rock concert? I guess when those people come out, they can't hear for a couple of days, right? And you see to have a threshold of pain, 130, by then your ears actually can become permanently damaged with that level, right? I think I think I did Google. Let me see something. The decibel meter. Let me see. The decibel meter actually uses a different formula. Let me see what they use just now. Give me a second. I just want to show you what the decibel meter actually does. Their formula is a little different. The decibel meter, I think is they use L equal to 20 log of, they use P, root mean square, over PO, right? And well, you don't have to know this, right? You don't worry nothing about this in for your course. I'm just telling you, this is the formula they use, right? And I think they use the reference level is PO, P subscript O is the, yes, they say what they call acoustic air, meaning normal air, then what they call ambient air, the air around them. They use that so as the reference, right? You don't have to know this. Don't worry about it, right? And they use that to actually, let me see. Yeah, I think that's what they use. P subscript O is actually, I'm trying to figure out what they said here. PO. No. PO, it's not ambient ear, sorry. PO, they said here, this is what the internet says, right? That it's actually the pressure of 20 micropascal, right? And it's called the threshold of hearing. Threshold of hearing. That's what they use as the reference. That's the reference they use. It's 1,000, roughly around 1,000 hertz, right? Threshold of hearing at 1,000 hertz. It's this amount of pressure, right? So this is the formula they use. So this is the sound, the pressure of the sound that you're measuring, right? And the meter would actually measure that and compare it to the reference is 20 micropascal. And they multiply it not by 10, but 20. And they will actually give you a reading, right? And they call it a sound, what is it? Sound pressure level, decibel, sound pressure level, something like that. And they give you some examples, of different songs in the ear. Yeah, no, you don't concern yourself with this. This is not our course, really. Good. So we'll stop there. We talked there about the two different types of waves. A few things that you need to know about waves: their wavelength, their frequency, the period, amplitude. We talk about transverse waves, longitudinal. We got examples, and then we went on to sound waves, right? Sound waves, and sound waves. We said it's a special longitudinal waves. It makes all hearing possible, right? And something I probably didn't mention about sound waves, it needs a medium to transmit. Electromagnetic waves, no medium is needed because electromagnetic waves come from the sun, light, heat, all those are electromagnetic waves. We call infrared waves are heat waves, right? They don't need a medium because space is a vacuum, yet they reach us here on the earth. But sound, you need a medium for sound to be transmitted, right? You need a medium, whether it be air, sound can travel through water, right? Can travel through water, it can travel through a solid piece of metal, it can travel along it, right? You need a medium for sound to travel. It's the most famous longitudinal wave. And then we talked about in particular the sound intensity, right? If I'm to go back to these are some values, right? The intensity level, right? And you can always go back to the notes, right? And they tell you, well, look, they tell you what certain intensity levels are, and whether you should expose yourself. Of course, prolonged exposure can be dangerous, right? Prolonged exposure can be dangerous, and you can actually do the calculation. I think where is it? This is the formula here. This is the formula to calculate decibels, right? The intensity of the sound you are dealing with compared to a reference, I subscript O, right? And usually, as we said, sometimes that would be like the sound of ambient ear, right? Almost, well, it's not that we say no sound, right? 0 decibel doesn't mean zero sound, right? place is ultra quiet, and you can compare it and actually calculate the decibel of a song. Right? Good. So I think we covered quite a bit there for this evening. We'll take up we'll switch over to light. The next day we'll talk about mirrors and so and lenses and so the next day. And I think we'll have to do another assessment next Tuesday. Because we have to we only do 2, we have to do 5 before the course ends. So we might have another one on Tuesday based on what we do last week, momentum and impulse, and then waves and song, right? I'll think whether I'll include
Sir,
anything
so
on
before you go ahead, or before we go ahead with our third test, would we get the results for the second test? Also, I noticed you removed the grades for the first test. Could you advise on that, please?
Yeah, as I said, I had to hide it because people, some people, when they come on to do the second assessment, they're confused. They're going into that assessment and so, right? So
So
that's why
when
I had
would you
to, yeah. I could
re-upload
actually,
it?
I could actually, because I think I gave everybody the last opportunity yesterday. Wait, let me make it public now.
Correct. Thank you
Um,
so much, sir.
yeah,
So we can know what
let me
we're
stop the
working with for the
recording.
third exam.
Yeah, sir. You
Yeah.
could release it now.